Hi! In the previous video, we have settled the fast inverse square root algorithm. Now we can code. Let's start with the basics, see code for Hello World and straight after that the standard library math.h. Well, that's as easy as it gets. A good warm-up. So the next easy thing is to try this machine instruction. I redefine res so that GCC does not optimize it. First, I expose the function to the C linker with .global. Then I mark a label to locate the function in the code. Next, the instruction and ret to return the result. Heavy commenting is important in assembly because it's a bit hard to decipher. Here are the compilation and test. So far, so good. To be complete, let's try the C fast inverse square root function. A quick copy-paste. And the test is successful. The main theme of this video is the implementation of the fast inverse square root function in assembly. Let's look at the C code once again. I can't see much, let's zoom in. As we have seen in the previous video, the code implements the Newton-Raphson iterative method for nonlinear equation solving. The part of the code that realize the iterations around the first approximation of the solution. And the first approximation of the solution is performed by the float integer representation logarithm trick. Therefore, we have operations on floats, operations on ints, and constants. Let's start by defining the constants that we will need. I usually put them at the end of the source. 1/2 and 3/2 are floats. And the special constant is a 32-bit integer. This is called a long type. With that done, we can expose our function to the linker with .global and start coding this function. It's a matter of adapting each C instruction to assembly. The first is float, thus we start with the float tract. We load the constant value in the XMM1 register. When calling externals from C, the float argument will be in XMM0. Then comes the multiplication instruction. Mul_s is a simple one. Multiplier, scalar, single precision. Basically take this XMM register and this XMM register, multiply them, and put the result in the second one. We proceed with the next part of the Newton-Raphson iteration. Again, a matter of copy-pasting the C code. In assembly, instructions do not combine, we need to simplify this complex multiplication. Now, from the C code, I see that y comes from the integer tract. I'm going to assume it will be located in XMM2. 2 multiplications mean 2 mul_s instructions. Then 1.5 minus. We start by loading the constant and then subtract. Let's not forget the last multiplication before returning the value. We are missing the integer tract that defines y. First, interpret the bits of the float as integer. We simply copy over the bits of the float that are in XMM0 to a general-purpose 32-bit register. The XMM registers are used for vectorial float operations. The EAX registers are general-purpose registers. They can be used for integer arithmetics. We break the swearing operation into 2. And we shift the register 1 position to the right. We load the number into the ECX register. We avoid EBX because it is a special non-volatile register. Then we perform the integer subtraction. And return the result to float in the XMM2 register where the float tract awaits it. We should be about good. Before compiling, I quickly fix this %sign I forgot. And test. Well, silly me, I forgot to call it from the C program. Let me try again. The exact inverse result of what we expected. Inconceivable. Having worked through the algorithm helps my dizzying intellect guess where the problem is. We likely have fallen victim to one of the classic blunders, the almost most famous of which is never going against a Sicilian when death is on the line. But only slightly less well known is this: if the result is the inverse of what we expected, then we are likely to subtract in the wrong order. This is not to be truffled with. In the instruction mollis s eximum 1 eximum 0, I took on that the operation was performed in the order of reading. This is incorrect. In this case, xmm0 is indeed the destination, but the operation is performed in this order. We can verify this if we test in isolation the assembly subtraction instruction. The easy solution to this erroneous result here is to invert the number. For a float, this is easy. Recall for IEEE 754 float number, the first bit is the sign. We just need to flip it, which we can do with an exclusive OR, as is shown here in the truth table. Maybe it's more evident in this example. In the code, I start a mask for XOR inversion. I will need to align the memory addresses of the constant because here the bit position is important. The eximum register are 128-bit registers for multiple parallel computation. So I mask only the first number and leave the others unchanged using a zero mask. And now the assembly function works. This is all well and good, but this is not the algorithm as we have seen in the previous video. This is a hack to correct a small mistake. So let's indicate it by an explicit comment, and proceeds to try to make a clean implementation. We start by taking care of the C calling. Then we copy over the hacky function. Remove the hack. Now we will want to have both 3 halves and the result in eximum 0. So a bit earlier, we copy y in eximum 3. And then we can adapt the subtraction to obtain the correct result. If I remember well from the external call video, it's only slightly longer than the hack because it has 1 instruction more. Even though counting instruction is not a 100% valid way of evaluating a program execution. Well, that was my implementation of the fast inverse square root function in assembly. This is the end of this video. Thanks for watching. See you next time. Or stay for a message from the sponsor of this video. Me. I'm the sponsor of this video. Get some rest. If you haven't got your health, then you haven't got anything. Even if you have your country's 500th anniversary to plan, your wedding to arrange, your wife to murder, and the neighbour to frame for it. Bye now.